Hello guys, and welcome back to the CCNA video series brought to you by ABY Design and Tech. In this video, we're going to have a look at the different types of IGP routing protocols. The learning objectives for this video are as follows: to understand what the different types of IGP routing protocols that exist, to understand how they work, and to be able to list some of the IGP routing protocols that we have today. So before we go any further, let's just recap what we covered on the previous video. So, an IGP routing protocol is a routing protocol that allows routers that belong to the same autonomous system, the same company. It allows those guys to exchange routes, and is used by each router to build a routing table and work out the best routes to reach each network automatically. So with dynamic routing protocols, the routers, they do everything for us. We don't have to do a thing apart from enable the routing protocol on that device. Instead of us having to manually go in and configure every single route manually and then change the routes when something changes, no. The routers do all that for us and we can sit back and relax. Now, the way that these IGP routing protocols work to achieve their goal will differ depending on whether they are link state routing protocols or distance vector routing protocols. So these are the two different types of IGP routing protocols that we have today. So let's dive in. Link state. Let's start off with link state first. So with a link state routing protocol, each router has a full picture of what the network looks like. Basically, they have a network topology diagram stored in a database in memory, and once they have built this picture of what the network looks like, and by the way, every single router will have that same picture, they'll all have the same picture of what the network looks like, they then run an algorithm known as the shortest path first algorithm on that network topology and work out, from my point of view, what is the best route or the best path to reach every single network in this enterprise, and they do that by using the SPF algorithm. Now, to build this picture of what the network looks like, essentially our devices will exchange something known as LSAs. So LSAs, which stand for link state advertisements, they include essentially three pieces of information. So obviously it's going to include some sort of identifier for who generated the LSA. So it will essentially identify the router which generated this LSA so that we know who he is. It will list information about the link. So in this case, all of the interfaces on the router. It will list information about maybe its IP addresses, and most importantly, it's going to list information about that router's neighbors. And so think of it like this: each LSA is a piece of a puzzle. So the way that it works, every single router in your network will be generating a LSA to explain itself, and they will be flooding those LSAs so that every single router has got every single other LSA. Once a router has got all those LSAs stored in its database, well, guess what? He's like, I've got all the pieces of the puzzle now. Guess what I'm going to do? I'm going to rearrange those pieces of the puzzle, build that network picture, and guess what? I know exactly what the network looks like. Now, all I need to do is look on my map, look at my network map, look at that picture of the network and work out, to reach this network, which best path do I have? So I can go via this guy, I can via that guy, but wait a minute, this route, this path, that is my best path to reach that network. Okay guys, so this is what our network topology looks like. So as you can see, pretty large network topology. Again, this is why we would use dynamic routing protocols, because if we try to configure static routes, but guess what? Apart from these networks which R1 connects to, we would have to tell them how to reach all of these other networks. And even this sort of scenario is going to be a pain in the backside. Let's say something changes, then we have to go and reconfigure static routes for every other for every other device as well. Well, with link state routing protocols, this is what our network looks like, and this is what R1 sees. So as you can see, R1 sees the entire network. He sees the picture of what the network looks like, the entire network. Nothing is hidden from him. He knows everything. So the way that this works is that each router, let's take R9 as an example, R9 will generate a LSA. In that LSA, he would have a identifier to identify himself, saying that, look, it's R9 who generated this LSA. Now within that LSA, he will list out each one of his interfaces, the IP address associated with that interface, okay? and also any neighbors that he has. So in this case, R1 knows, well, okay, R9 has a connection to 172.16.10/24. That is probably going to be a connection to a subnet with a bunch of end users because he doesn't have a neighbor on that link. However, R9 over these links over here connects to R8, R6, and R5. So they must be point-to-point links, or they must be links to other devices. And so every router will essentially just generate a LSA describing the exact same thing. So in this case, R6, when he generates his LSA, he will list his interfaces. And again, they only list the interfaces that the routing protocol is enabled on. So with Linkstate routing protocols, the only interfaces included in the LSAs will be the interfaces the routing protocol is enabled on. So in this case, R6, he will list, okay, I'm R6, these are my interfaces, these are the networks associated with those interfaces, and these are my neighbors, etc. And so essentially, once R1 gets all these individual LSAs, each piece of the puzzle, he can then rearrange them, okay? So he's like, okay, R9 goes here, let me put R6 over here, okay, R5 goes here, let's take, okay, now, R4 goes over here. Okay, I think I've got the picture. Once he's built this picture of what the network looks like, he will then think, now that I've got the picture of what the network looks like, let me go and calculate my fastest path to reach every single one of those networks. And he can do that because he has the complete picture. And the biggest benefit of Linkstate routing protocols is that every single device has that same picture. They all know where everything is, they all know who their neighbors are, their neighbors' neighbors are, who their neighbors are, etc. They know everything. And this is one of the benefits, again, of Linkstate routing protocols. Because every router has got a complete picture of what the network looks like, it means that we're less likely to have loops because they know where everything is connected. One of the only issues is that with Linkstate routing protocols, this picture of what the network looks like, it has to be stored in the router's memory. Now, logic dictates that the larger the network topology, the larger that table or that picture would, the more space, that picture will take up in memory. So that is one of the caveats of Linkstate routing protocols, that the larger our network topology gets, the more memory this picture will take up in memory on the router. And also, the longer it will take for the router to essentially look at this picture and work out his best path and how to reach every single network. Now, the next type of routing protocol we have, or IGP routing protocol, are going to be distance vector routing protocols. So distance vector routing protocols, they're very different from Linkstate in that the router only knows two things about each route. So the biggest contrast is that distance vector, we don't build this picture or this map of what the network looks like. We don't do this. We learn about these routes through other means. So every single a router knows two things about every single route. In this case, it would be distance, which is how far away that network is. So essentially, the larger the metric, the less preferred that route is to, let's say, a route which has a lower metric to that same network. So as an example, just to whiteboard this very quickly, imagine we have R1 over here. Now R1 has got two routes to reach a network X. Okay, this route via this way, and a route via this way. Let's say that this route has a metric of 50. Let's say this route has a metric of 30. Well, guess what? R1 is going to prefer this route because it has a lower metric. He thinks this is a quicker path to reach network X than this guy over here. And so he will then start forwarding traffic to network X over this path. So as well as knowing distance, so the metric of the route, a router will also know vector. So the vector is just which interface and which next hop do I have to go through next to reach that network. So a router knows only those two things about each route. Each router has a partial view of what the network topology looks like. They just know about their neighbors and what networks they can reach through their neighbors. So again, this is different. So with distance vector routing protocols, each router does not have a complete picture of what the network looks like. All they know is, okay, these are my neighbors, and these are the routes, or these are the networks that my neighbors have told me about. Well, because they told me about them, I can reach those networks through my neighbors. So now I believe them because I've got no other information to go off. That's how distance vector routing protocols work. And then commonly referred to as routing through rumors. So essentially, we're routing traffic based on what our neighbors have told us. There's no way for us to really confirm, but we just have to believe them because that's all we know. And that's the best information that we've got. So going back to our example network topology, this is what our network topology looks like. However, with distance vector routing protocols, let's take R1 as an example. R1 doesn't see this entire network topology, no. With distance vector routing protocols, R1 instead sees this. So this is what R1 sees. R1 only sees, in this case, we've only taken one neighbor, but obviously this would apply to all of R1's neighbors. All R1 sees is, okay, this is my neighbor, R2, and these are the networks that he has told me about, and these are the networks that I can reach through him. He doesn't know that R2 doesn't have a direct connection to those networks. All he knows is, okay, these are the networks R2 has told me about. I believe him because I don't have any other information that I can use. So now I'll be sending all of my traffic to reach those networks to R2. And that is distance vector routing protocols in a nutshell. So as you can see, there is a massive difference. Now, one of the benefits of distance vector routing protocols is that we don't have to spend a lot or use up a lot of memory on the router to build this massive picture of what the network looks like. The caveats of distance vector routing protocols are that it's more likely to have loops because we don't know anything beyond our neighbors. All we know is, okay, these are my links to my neighbors. These are the networks they have told me about. I believe them, but we don't know. So R1 doesn't know what the network looks like beyond its neighbors. He doesn't know what the network looks like beyond R2. He doesn't know anything about that, which means that the chances of having a loop in our network with distance vector routing protocols is a lot more than with link state routing protocols. Now, distance vector routing protocols like EIGRP, there are certain mechanisms they put in place to stop loops, but that's beyond the scope of the CCNA exam. For now, it's just important to know that with link state, we have a complete picture of what the network looks like. With distance vector, all we know is who our neighbors are and the networks that our neighbors have told us that we can reach through them. So all we know is, okay, these are my neighbors and these are the networks my neighbors have told me that I can reach through them. Now, let's have a look at the different types of routing protocols. So we have link state. Some examples are OSPF and ISIS. So that's intermediate system to intermediate system. Sorry, guys. So ISIS, that would be used in a kind of a data center service provider environment. OSPF, that can also be used in a service provider environment, but typically OSPF is used in an enterprise environment. Now with distance vector, the two main types of distance vector protocols we have are EIGRP and RIP. So EIGRP, that stands for enhanced something protocol. So enhanced in. To be fair, I forget the name, but the most important thing to remember is that OSPF, that's open source in terms of that is vendor neutral, which means that we can use it with any vendor. So HP switches support OSPF. Juniper switches support OSPF. Cisco switches, yeah, you heard that right, support OSPF. Now with EIGRP, that's a Cisco proprietary protocol, meaning only Cisco devices support EIGRP. RIP, again, that is vendor neutral, so we have different devices supporting RIP. Okay, Abda, so which one's better than which and which ones do I use? But to be fair, it just depends on your environment. This is why I put this slide as different flavors, because essentially it just depends on what you prefer, what you're more comfortable with, and what's going to be used in your environment. To be fair, OSPF as a link state protocol has some benefits that maybe EIGRP doesn't have, and there are certain things about EIGRP that are better than OSPF. So again, it just depends on your environment. Now, this debate between which routing protocol is better than which, I like to compare this to the debate of who's the best soccer player or who's the best football player. Again, it just depends on people's taste. Some people like Cristiano Ronaldo, some people like Messi. Again, it just depends on that person's taste on who they think is the best, and is exactly the same with routing protocols. It just depends, okay, I prefer OSPF or I prefer EIGRP, etc. It just depends on the person. So guys, we have reached the end of this video, and just to recap, we have covered the different types of IGP routing protocol. So link state, I know everything. Distance vector, I only know what my neighbors have told me in this routing through rumors. We've also looked at some examples of some link state and some distance vector routing protocol. So RIP, EIGRP, which are distance vector routing protocols. And then we've also got link state routing protocols like OSPF and ISIS. If you found this video useful and would like to see more content like this, then please subscribe to my channel, and thank you very much for watching.